Hello, Chem 1B. This is Chapter 15, Lecture Video 3, and we're going to be talking about Le Chatelier's principle. Le Chatelier's principle, this is kind of our full-on textbook definition of it. It says that if a system at equilibrium is disturbed by a change in temperature, pressure, or concentration of a component, the system will shift to counteract the disturbance. I like to think of Le Chatelier's principle like the teeter-totter of equilibrium reactions. In other words, what this statement's really saying is if we have a system that's at equilibrium, it's all happy, sitting at equilibrium, and we do something to push it out of equilibrium, it's going to do everything it can to counteract that action. In other words, it's going to try to get back to equilibrium. Now, depending on how we disturb or affect the equilibrium, it will shift towards either the reactant side to counteract that or the product side to counteract it. And depending on what we do affects which way it will shift. So we're going to first talk about concentration. Concentration is by far kind of the simpler thing to understand, I believe, in my opinion. And so let's say if I increase the concentration of H2, right? I have the system, it's at equilibrium, and all of a sudden I push it out of equilibrium by adding more H2 into the system. Now, what that's going to do is it's going to increase the concentration of the reactants because H2 is on the reactant side of this equilibrium. Now, how can my reaction minimize or counteract that disturbance? Well, it will shift towards the products, right? By shifting towards the products, i.e. making more products, the concentration of our reactants will start to come back down. The concentration of my products will go up, and we'll eventually get to a point where we're back to equilibrium, counteracting the increase in concentration of H2 that I did. In other words, the equilibrium when I increase the concentration of H2 in this scenario is going to shift towards the product side. Now, if we want to really think about this in terms of kinetics, what's happening when I increase my concentration of H2? Well, the forward rate of my reaction is going to be going faster now. The reverse rate is going to stay basically the same. Well, in order to get back to equilibrium, these two rates have to be equal. And so as the forward rate is faster, it'll slow down as our reactant concentrations decrease and our product concentrations increase, as well as our reverse rate increasing as our NH3 concentration increases due to this whole thing, the shift. And eventually we'll hit back to equilibrium. So it also can be seen from a rate perspective as well. Now let's look at one more concentration thing before we kind of talk about how to tell which way it's going to shift a little bit more. If concentration of NH3 is decreased, right? So let's say I'm taking my concentration of NH3 and I'm bringing it down somehow. Maybe I put something in to get rid of it. Maybe I took some of it out, whatever. I decreased its concentration. Which direction will the equilibrium shift to counteract that? Well, if I got rid of NH3, the equilibrium, to get back to being at equilibrium, the reaction has to produce more of NH3. So again, our reaction is going to shift towards the product side. This will increase the NH3 and it'll also decrease these guys. But eventually we'll get back to equilibrium having counteracted this decrease in concentration. So really there are two rules with Le Chatelier's principle and concentration. And that is that if we decrease the concentration on one side of the reaction, doesn't matter which side, whenever you decrease a concentration, the reaction is going to shift towards the side of the reaction that you decreased a component on, right? So I decreased NH3 here in the second example. It shifted towards the products. NH3 is a product. Because I decreased the concentration of a product, I'm going to shift towards the products. If instead I had said I decreased the concentration of N2, we're going to shift towards the reactants because I decreased a reactant concentration. The opposite, if we're increasing a concentration, we shift away from the side that we increased on, right? In the first example, we increased the H2 concentration. This caused a shift towards the products. If I had an example on this slide where I increased the NH3 concentration, then we would have seen a shift backwards towards the reactants. So it really, when we're trying to figure out which way it's going to shift based on concentration, is really what are we doing to the concentration? Are we increasing it or decreasing it? And on what side of the reaction did the increase or decrease occur? If it's an increase, we shift away from the side it increased on. If it's a decrease, we shift towards the side it decreased on. So let's talk about how temperature or heating a reaction affects our equilibriums. Now, when we heat a reaction, basically we're raising the temperature of it, right? So if I add heat to this reaction, is heat going to be a product or a reactant? One of the things we have to care about when we look at how heat or temperature is going to affect our equilibriums is our delta H of the reaction, given here in this reaction. Now, really all we care about is whether there's a positive or a negative sign for our delta H. Remember, enthalpy can determine whether our reaction is endo or exothermic. And if you don't remember these definitions, we learned them in Chem 1A, right? But endothermic means that the reaction is going to absorb energy from the surroundings. And exo means it's going to release energy from the surroundings. Now, when a reaction has a positive delta H, that means it's an endothermic reaction. And when it has a negative delta H, it's an exothermic reaction. So given all that, we know our delta H here is greater than 0, meaning positive. So given the definition of an endothermic process, where would we consider heat to be? Is it a reactant or a product? In this case, heat's going to be put in. That's what it means when you have an endothermic process. It's absorbing energy from the surroundings in order for the reaction to occur. So heat we can kind of consider as a reactant. It's not technically a reactant. It's not a substance. It's more just energy. But it still would be technically on the reactant side. So whenever we look at how heat is going to affect or temperature is going to affect our equilibriums, we need to figure out which side of the reaction it would be on, right? In an endothermic situation like this reaction up top, heat's going to be pretty much a reactant. In an exothermic situation, it's going to be the opposite. In exothermic reactions, heat is being released. That means it's a byproduct of the reactant. It's being produced. So heat would be on the product side. Now, heat and temperature effects are pretty much identical to concentration. If we increase the amount of heat present, it will shift away from the side that we consider heat to be on, right? So if I heat this reaction up, because it's an endothermic reaction and heat is on the reactant side, I am basically increasing a reactant, which, as we learned on the previous slide, means we're shifting towards the products. Whereas if I increase temperature for an exothermic reaction, I'm increasing a product, which means I'm going to shift towards the reactant side. And the opposite is true of decreasing, right? If I'm decreasing heat, I'm decreasing a reactant. My reaction is going to shift towards the reactants for endothermic. Or if I decrease an exothermic reaction's temperature, I'm going to be shifting towards the products. All right, so what is favored if the reaction is heated then, right? As we kind of discussed in the previous, our products are going to be favored because as I increase temperature, I'm effectively increasing a reactant, which is going to cause a shift towards the product side. And if I cooled this reaction, well, then I'm decreasing a reactant, which will cause a shift towards the reactant side. Now, in our Le Chatelier's principal lab, you're actually going to be seeing this exact reaction occur, and I've color-coded it appropriately. The reactants in this reaction are actually a reddish color, and the products are actually a very deep blue color. So when we heat or cool it down, you're actually going to see the color of the reaction change due to the fact that our products and reactants are different colors. And when we cool a reaction, we're effectively removing heat or decreasing the temperature. Now, in reality, heat's not actually a physical substance. So what's actually happening here is as we change temperature, our equilibrium constant is changing as well. When we increase the temperature for an endothermic reaction, its equilibrium constant increases in value, which means the products are more favored. And when we increase the temperature of an exothermic reaction, its equilibrium constant decreases in value, which means the reaction is becoming more reactant favored. So here's kind of a picture of what you're going to see in the video. When we're at room temperature here, it's kind of like a purplish color. That's because we got some reactants present, we have some products present. But as soon as we start heating the reaction, you kind of see this purplish color goes to like a very blue color. This is because there are less reactants present in the heated solution than there were in the room temperature solution. And if we cool it down, it goes the other way, right? We shift towards the reactant side. The reactants are red or pinkish, and we have very little products present at the low temperature. So this is like an ice bath, and this is a hot water bath. Do an example here. We have this reaction, right? We have a solid substance here. We have these two aqueous products here. What happens if I add HCl? Now, this is kind of taking what we've just learned about concentration and applying it now. If we add HCl, what's going to happen? The acid is going to react with our base, right? Our HCl is going to react with this OH minus in solution. Now, what does that mean? Well, that means the OH minus concentration is going to come down, right? As the reaction, the acid reacts with the OH minus concentration decreases. So what's going to happen to this equilibrium then? Well, if we have a product concentration decreasing, we're going to see a shift towards the product side. If instead of adding HCl, I added NaOH, we'd see the opposite. Now, in this case, this is what we call a solubility equilibrium, which we'll get to in chapter 17. However, this is a solid, and calcium hydroxide is a white solid. So when we initially just have a solution of calcium hydroxide, you're going to see a bunch of insoluble white solid present in water, and it's going to be murky and white. Calcium ion and hydroxide ion, they're both clear solutions. I put them as gray because I obviously can't make them clear, then we wouldn't be able to see them. But they're clear. So if we do this and the reaction shifts towards the products, what we're going to see is the solution is going to turn clear because it goes from a cloudy substance to a clear substance because we're getting rid of a lot of the reactants. Now, if we add NaOH, the opposite is going to occur, right? By adding NaOH, I'm effectively, let's use a different color, I'm adding OH minus. This time, I'm increasing this guy. I'm going to see a shift towards the reactant side. This means the reaction is going to precipitate more calcium hydroxide out. We're going to see more white solid form. And you should be able to explain things like this yourself on a test. So let's look at this reaction. Now we're going to talk about how pressure, this last component that we talked about in the beginning slide, affects our equilibrium shifts, right? Pressure is a little bit interesting. It's different from the other two. When pressure is reduced, the reaction, in this case, this reaction, that's an ugly color, let's use a different color, this reaction is going to shift towards the products. Let's think about why. When we change the pressure in a container, and that's what we're doing, we're not changing an individual pressure of any one component in this reaction, we're changing all the pressures of every component in the reaction. And that's going to have some interesting effects, right? So we need to really compare the moles of gaseous products total to the moles of gaseous reactants. In this case, we have 2 moles of gas here on the reactant side, and we have 3 moles of gas on the product side. Now, when I increase pressure, because I have more gaseous products, I'm really increasing products more than reactants. Or if I reduce pressure, I'm doing the same thing. I'm reducing my products more than my reactants because I have more gaseous products than I have reactants. For this reason, if pressure is reduced, we see a shift towards the product side. We can reason this out at the molecular level. The products are going to, by reducing pressure, we're creating more space between molecules. And in order to get that spacing back to where it was at equilibrium, we need to increase the number of molecules present. There are more gaseous products than there are reactants, so we shift towards the products. We also see that that our rates are changing as well, right? By increasing pressure or reducing pressure, we're affecting the rate of the reverse or forward reaction differently based on the moles and order of the reaction that is occurring in that situation. Again, this is always a non-equilibrium condition reestablishing equilibrium. We're always talking, when we're talking about Le Chatelier's principle, we're talking about pushing equilibrium out of equilibrium and then watching what happens in order to get back to equilibrium. Again, at the end of the day, as far as rates go, once we reach equilibrium, again, after the shift occurs, we're back to the forward and reverse rate being equal to each other. Okay. Let's talk about this again, right? So what is favored in the following reaction when pressure is increased by reducing the volume of our container, right? We know that when we reduce the volume of a container, pressure inside the container is going to go up. That was one of the gas law relationships we learned in Chem 1A. So because I know that I have 2 moles of gas on this side and 1 mole of gas on the product side, this is what or reactant side, sorry, we need to look at when figuring this out. When I'm looking at this, I'm going to increase pressure. So in other words, I'm really increasing my product side more than my reactant side because of the fact that I have 2 moles of gas on the product side and only 1 mole of gas on the reactant side. This is going to cause a shift towards the reactant side. In other words, we're going to produce more N2O4. All right, let's do a couple more problems and then we'll end this video, right? Le Chatelier's problem, so which change will cause more CO2 to form in a closed container? Our delta H is 136 kilojoules. The important part of this is that it's positive. And we have this reaction, we got a solid, we got a solid, we got a gas, we got a gas. So let's look at what's going to happen. We want to form more CO2. In other words, we want the reaction to shift towards the product side. So what of these will cause that, right? So let's look at water. If we increase the concentration of water or the amount of water, that's going to cause a shift towards the reactant. So we don't want this one. That's not right, all right? Let's see about removing sodium bicarbonate. Well, this is in the solid state, meaning its concentration is constant. Removing it doesn't change its concentration, which means it doesn't affect our equilibrium. So that one's wrong. The same argument can be made for sodium carbonate. It's a pure substance, pure solid. Solids have constant concentrations. In changing its concentration is not going to, or changing the amount of solid present is not going to affect its concentration, and therefore not going to affect the equilibrium. Increasing the pressure of our container, this might work. So let's look. We have 1 mole, 2 moles of gases on the product side, and 0 moles of gas on the reactant side. So what will increasing the pressure do? It will cause an increase of the products, and again we see a shift towards the reactants, which again is not what we want to do. So that can't be it. So what about increasing the temperature, heating the temperature? Well, remember it's an endothermic reaction. So let's see if I can pick another color here. That means really heat is another reactant. So if I increase temperature or heat the container, I'm increasing heat. This is going to cause a shift towards the products. Hey, that's what we wanted. This is my correct answer, E. All right, so one last topic before we get going here and finish this video. we just talked about Le Chatelier's principle, and it's kind of the qualitative method of predicting which direction a reaction will shift in order to get to equilibrium. However, Q is our quantitative method, right? So looking at numeric values to determine this. And this is honestly often more valuable. So in order to do this, what we need to do is be able to calculate what we call the reaction quotient, or Q. It's pretty much calculated exactly like the equilibrium constant here, just using initial concentrations instead of equilibrium concentrations. Or maybe it's equilibrium as well, and we just don't know their equilibrium concentrations yet. We then take our Q value and we compare it to K. If Q is greater than K, the reverse reaction is going to occur to reach equilibrium. In other words, we're going to shift towards the reactants. We're not at equilibrium if Q is greater than K. If Q is less than K, then we need the forward reaction to occur to reach equilibrium. Again, the reaction is not at equilibrium yet. This means we're shifting towards the products. And if Q is equal to K, then we are at equilibrium and everything's good. Again, the way we calculate Q, like I said, for any equilibrium is it's just really calculated the same way we calculate our equilibrium constant, except using initial concentrations or concentrations we know aren't at equilibrium or don't know if they're at equilibrium one way or the other. So let's do a problem with this. We are going to use the synthesis of ammonia, has an equilibrium constant of 1.2 at 300 Celsius. Will the reaction shift towards the products or the reactants if initially these are our concentrations? So we need to look at the ammonia synthesis, right? That's N2 plus H2 goes to NH3. We got to balance this, and this is what we get, right? So my equilibrium constant, or my Q expression, is going to be equal to NH3's concentration squared all over N2's concentration times H2's concentration cubed. And I was given K, right? KQ here is equal to 1.2. We want to calculate Q so that we can compare it to K to determine which direction the equilibrium is going to shift. Right? So we just plug in these values for Q, right? We know we have 0.48 molar NH3, and that's squared. We have 0.6 molar N2, and we have 0.76 molar H2, and that has to be cubed according to the equation. And then we can calculate this value and compare it to the K. All right, so the value we get for Q is 0.875 effectively. We can then compare this to K. We know 1.2 is greater than 0.875, or in other words, K is greater than Q. This tells me effectively which direction my reaction is going to shift. It basically tells me that since Q is less than K, my reaction is going to be shifting towards the products in order to increase Q, right? Because if we increase this value, decrease these values, the value is going to go up. All right, so that's the end of this lecture video. If you have any questions, please come to the discussion sessions or email me.